Hello everyone, welcome to this webinar on adaptive programming. My name is Jesse Stark, HVAC Channel Manager. Let's get started. Looking at an agenda of what we'll be covering in this topic, first we'll be going through an introduction and how to get started with adaptive programming, and then we'll spend the rest of the time looking at all the different function blocks that are available to build an adaptive program. So what is adaptive programming? Adaptive programming is a full-fledged function block editor that's built into all of the 80 series of drives that ABB has to offer. So this would be part of our all-compatible portfolio of products, including the ACH580, the ACS580, the ACS880, and the ACQ580 products. There's a total of 32 different function blocks that you can be used to build up a function block program. And you can build lots and lots of different basic controls. In my case, I'm listing some HVAC applications here, but there's no reason why you couldn't be using these for industrial and water type applications, cooling tower, multi-stage controllers. I actually have a good example of how to do that that we can run as a follow-up and provide some materials for on building a multi-stage cooling tower controller. You can use it to do some advanced damper interlock, do exhaust and velocity OAD control with laboratory exhaust, and then doing some advanced timers. These are really basic functions that we're putting into the drive, but if you didn't have that capability in the drive, you'd have to be adding external timers and relays, or maybe even a PLC or a building automation system where maybe you might not want to make that investment. So this makes it a lot easier, a little less expensive. Something to note is that adaptive programming is built in to Drive Composer. So previously, when we first launched this, adaptive programming was available only as part of Drive Composer Pro, which is the paid-for license that comes with that software. We have now since expanded it that both the entry and pro versions allow you to build and load adaptive programs on there. So when you first boot up Drive Composer, you'll be introduced with a welcome screen like you would normally see. In the case of today, we're going to walk through doing a quick demo because we don't have a drive in front of us. So a couple of the tips that I have here: if you don't have that drive in front of you, click that demo button in the bottom left-hand corner of the window. You'll be able to do all the programming that you want and test it out. But just be mindful that you cannot use parameter inputs or outputs, all of that, because I don't know which drive I'm actually talking to. None of that's specified. The biggest issue with this is saving the file and trying to load it later into a drive will result in a compatibility error. Essentially, I'm building up a program for a fake drive, doesn't exist, so when I start talking to a real drive, the program breaks. So don't spend a lot of time building programs in demo mode. Try to make sure you're connected to a drive at least once. Once you get that connected to, it's very, very easy to build up the programs. The other thing to note, that if you do demo mode, you will see I/O and data storage items that might not be available on the ACH580 or some of the 580 series. It could show some extra data storage that would only be available in the 880. So just be aware that building something up that might work and you've tested it, you will probably have to rebuild it if you haven't built it for the drive itself. All right, so now we've gotten in, we've either connected to our drive or we're working in demo mode. Up in the top left-hand corner, what you'll see in Drive Composer is a little right-hand arrow next to that All Drives piece. If that menu is not out, it'll be collapsed down to the left-hand side. You can click that arrow and it'll pop it out and you'll start seeing the menu down below where you'll see your drives and the list of drives you're connected to. In my case, I'm connected to a demo drive. Once I see the list of drives I want to use, I can right-click on the drive, which pops up another menu, and from that, I'll pick the fourth option down, Adaptive Programming, which will ultimately open up the adaptive programming screens within Drive Composer Pro or Entry. Once we get into adaptive programming, we'll see an interface something like this. This is a shrunken down version, so it can be seen on the screen. And we'll talk a little bit more about each one of these sections in a few minutes. But I'm going to highlight a couple of the areas, and then we'll talk about those in more depth a little bit later. First, the program tools. This is the area where you do your basic stuff. You're going to open files, save files. You can undo, redo, all sorts of different things to make it that your basic stuff. This is going to be like your file menu in any application you've ever used before. It's used for you to save the program and then come back to it later on. Next, you have the input section, which is down in that bottom left. It's going to be anything that goes on the left-hand side of the blocks, and we'll get into the anatomy of what a function block is and how they work a little bit later, so that'll make more sense. But any of you that have programmed with function block editors in the past, like LabVIEW, this will make a lot of sense. This is just everything that goes on the left side of the blocks. We follow that up by the outputs. That's everything that goes on the right side of the blocks and is an output of whatever function we run through. Top part, you have the actual list of function blocks available to you, broken down into sections like arithmetic blocks, logical blocks, selection blocks. So you'll see them all. That scrolls to the right, left and right. And then the last section is the programming area in purple down below. So let's talk a little bit more about what each one of those are. First and foremost, that blue section, bottom left, input section. It's a predefined list of inputs for getting information from the drive and I/O to using the adaptive programming. Pretty straightforward. Everything that's an input will always go on the left side of a function block. We follow that up by the outputs. I'm going to go down on the screen. We have a predefined list of outputs. You know, go figure. So it's the stuff that goes on the right. We've already talked about that a little bit. Function block menu, that's at the top. It's all of your options available to you. You just grab the one you want, drag and drop it into the programming area, which is down below in that purple section. It's the area where you build up your function blocks and connect them all together. Here are some things to consider. These are limitations and known issues of adaptive programming. So I always like to share these ahead of time just so people don't jump into the deep end thinking this is going to solve a problem and then it ultimately creates new problems for you. So first and foremost, field bus communications. There's no drive-to-drive communication capabilities within adaptive programming. I can't go and query another drive, grab that information, and utilize it in my adaptive programming. I also would need a building automation system to read and write to storage items if I wanted to talk between different drives. So what that means is the building automation system would talk to drive 1, write something into the data storage, and that could ultimately be affected by something that happened with drive 2, but the building automation system is ultimately what is interpreting that information and passing that back to the drive to make that work. Program size, this one's a little funky. Maximum of approximately 20 blocks. This limitation is within the ACS880 drive, not so much on the 580 series of product. A lot of this really breaks down to each of those function blocks, as you stick them into the program, require a certain amount of storage size within the program. And within the 880 series, a lot of that memory is taken up for the programming for the drive. The 580s have a lot more capability for you to program additional features into it, but this is where it gets a little tricky. There is no indicator showing you if the file size is too large. It just won't load into the drive. So unfortunately, there's nothing there to make it clear that you've exceeded your size. What I recommend is you start programming and try to load it into the drive as frequently as possible. But if you start drawing out what you think your control scheme is going to be, and you start getting above that 20 block threshold, just be very wary that, or be aware that it might be too big if you're using especially the 880 series. But 580, you might be able to push those limits out to 30 and 40 blocks. I've built up some programs with that size, but it also really depends on the function blocks I'm using, as each one requires different memory limitations or requirements, I guess. Drive storage. The program itself is not stored on the keypad, so this is the adaptive program you're writing. So if you have a drive failure, control board fails, or the power section fails, you're either going to have to bring back that control module back onto the drive with the replacement, or you're going to have to reprogram the adaptive program into the software after you've swapped everything out. So just make sure that you're always able to load that back in. And then any of the HVAC folks out there using Eclipse bypass, you know that we talk to the drive using the Eclipse itself. That's all done over Modbus. Essentially, because the Eclipse is controlling everything, there are extreme limitations on what you can do when an Eclipse bypass is included with adaptive programming. You can add some extra functionality to the drive, but just beware that if the Eclipse itself is doing some of the control, there's really not a big, easy way to override what the Eclipse is trying to tell the drive to do. Let's go through a basic anatomy of the function block itself. So I have 7 different bullet points on the left detailing what the function block is. And then on the right-hand side, I have a basic AND function block with some inputs and some outputs, and we're going to break that all down. So first and foremost, there's the function block type. That's designated up in that top section with the 1 highlighted against it. In this case, it's an AND block. Very easy for me to see that. All blocks are going to be labeled in such a way that you'll see what the type is right across the top there. Next thing you'll see is a little flag up in the top right-hand corner. This is the order block will be evaluated. So what's tricky here is you can't tweak that number. You just have to move the blocks around. And every time you move the block around, you'll see red flashing all over the screen because all of the blocks are updating how they get evaluated. There are some instances where if you place the blocks in a certain way on the screen, you can actually have the order get all jumbled on how it evaluates things. Instead of being sequential, it kind of just bounces all over your adaptive program. So just be mindful of your order. You could end up in a space where you try to do calculations on something that had a dependent before that never ran its calculation yet. So be wary of that. Watch those orders how everything's going to be evaluated and move things around accordingly. Then you have 3 and 4. First is the inputs, the function block inputs, and then the function block outputs on the right. We've already hit on that a little bit. I want to show you the different types of fields there. One, you have that pointed, I'm going to say sideways house here, or arrow. Those are Boolean. They've got that turquoise color. Those are always going to be true-false type parameters or attributes or variables. And then you have floats, which are the rounded gold pieces. Those can be numbers. Typically, they can be plus or minus, and they typically are going to be 16-bit in length. So just something to consider. Each one of those function blocks have a puzzle piece shape for you to feed the right piece into it. So you can't necessarily feed a float into a Boolean input or take a float as an output when it's expecting to output Boolean. Now we're starting to get into some of the more advanced features that make programs a lot easier for you to read. Number 5 is the input and output labels. These are actually on both sides. It's that little yellow ribbon on the top. It says run enable, DI1, DI2. These are items that you can go in and customize the wording on just by double-clicking on that. You edit it, and then you can also add comments and descriptions for each of the things you're trying to accomplish here. Just a really good way for you to document your code, essentially, within a function block editor. Number 6 is that little gray bar on the bottom. This isn't on every single one of these function blocks, but in the cases where you can have more than just the inputs that are shown by default, that's something you can click and grab and drag down. And that'll make more sense as we start going through some of the function blocks. But ultimately, this is where you get to start seeing some of those optional inputs that aren't required every single time. And then number 7 is that little slash to the left of your DI. This is going to show up typically whenever you're pulling in a DI into one of your inputs on the left-hand side. And essentially, that's going to be high when closed, which is shown as that slash, or high when open, which is a circle. So that's just it's essentially like putting a not signal and flipping or inversing whatever the signal is to help with your logic. So, all right, we've already talked a little bit about the inputs and outputs, but let's talk about within those menu structures, the types of inputs and outputs. And you'll notice that the lists on both sides are very, very, very similar. There's going to be one thing that's missing, basically on the right-hand side, and it'll make sense when we talk about it. And that would be constants, right? I can't output anything to be a constant because my function block is ultimately doing the math to change that and make it a different output. So I can use constants as inputs. So that's like me setting a value of 5 or 10 or whatever, and that's always going to be the answer. A lot of times these are good for when you're using some of the filter function blocks or the PID function blocks, things like that. But ultimately on both sides, you get things like parameters. So I can actually go read the parameter lists for an input so I can see what something's set as. I can also write to the parameters if it's an output and tweak some of the settings. I also can read the I/O or even write to the I/O. So I can actually change the states of relay outputs if I use an output. I can read the state of a digital input if I use it as an input. Actual values are going to be readings of the drive, things like motor speed, output frequency, motor current, motor torque, and motor shaft power. These are all attributes which you can read directly from the drive. Also, you can output in some cases directly to the drive to change some of those values. Status is essentially, these are true-false type situations, typically telling you that the drive's enabled, inhibited, it's ready to start, tripped, at set point, etc. These are things you can, typically you're going to use them to read, but you can also change the status by writing to those signals as well. And the last piece is data storage. There's anywhere between 2 and 4 data storage points within each one of the drives for your adaptive programming. And this just allows you to write information to the parameters and use them in a custom way. In fact, in our example application that we can run through in a different training, we use data storage extensively to store bits into a parameter and ultimately have 4 additional parameters that we can program and tweak right from the drive keypad to manipulate or change our adaptive program. Now we're getting into some of the actual function blocks themselves, and the rest of this time is just going to be, for awareness, so that you know what's possible with adaptive programming. I'll talk a little bit about how each one of these work, but the expectation here is that you've got some programming background and knowledge, so I don't want to spend too much time explaining, what an AND or an OR is, but I want you to be aware of what types of function blocks are available to you when building an adaptive program. It's broken up into 6 different sections. There's the arithmetic or math blocks, there's the logical blocks, the selection blocks, comparison blocks, timer blocks, and operation blocks. And we'll go through each one of these in more detail, but ultimately, a lot of those are very, very self-explanatory, so I'm not going to go through that in too much detail, but this is a good summary of everything that's available to you, and it actually lists all the different function blocks as well under functions on this slide. So first and foremost, math blocks. You got your basics: add, subtract, multiply, divide, pretty basic. A lot of these actually have multiple inputs. We talked about that earlier, where you could have that bar stretched down. You see that bar on the add and multiply blocks because I can have multiple inputs where I can add them together or divide them together. But it gets a lot more tricky when I do things like subtract. Well, if I had 3 inputs, what do I do with the third input? Is that another minus? It's just something that you'll have to chain those together if you want to subtract multiple numbers. So you'll see that bar is missing there. And then the 2 other functions that we have for math blocks are the absolute value. So essentially it takes all negative inputs and turns them positive and keeps all positive inputs as positive. And then you have your square root, again, all very basic math. So I take the square root of 4 as my input, or I put the input as 4, would evaluate it as the square root, and I would have an output of 2. One other arithmetic block that I fit on that slide that requires a little bit more explanation, and that's the filter block. Essentially, you can take any input that you want and then run it through a single pole low-pass filter. So you take the input, plug it in. This could be a temperature sensor or a pressure sensor, anything I want, and then I specify a time for me to filter and take an average of what those values should have been over that amount of time. And we walk through the math there to essentially take the coefficient is the time level divided by the time level plus time, and then we run that past the in and the outs over time and come up with a filtered value. A lot of time what this is going to do is it's going to smooth out your signal, especially if you have a sensor that's kind of bouncing all over the place. You might want to run this low pass filter across your electrical signal. If it's doing like an analog input, it's usually going to be an analog input of some sort that you want to filter and make sure it doesn't just turn things on when it's not necessary. Next arithmetic function is the ramps. So this has got a lot of inputs here, so I'm going to walk through each one of these. But the essential reason you'd use a ramp function is to take your starting input and work your way to your final destination. So think of it like your acceleration or where you want to get with speed, and it would slowly change that over time, and you get to specify that time and the values that are there. So first is your input. the in, which is the reference value to ramp to the output. So in this case, let's say I wanted to ramp from 0 to 60 hertz. I might input 60 here. I could say the amount, then we have the increase or decrease. If I'm going from 0 to 60, I'm only going to use the increase. The amount of output increase per second. So let's say I wanted to go from 0 to 60 hertz in 15 seconds. I would ultimately do my increase as 4 because that's going to increase the hertz by 4 hertz every 1 second. By 15 seconds, I should be at 15. Tracking, essentially what this allows you to do, you set that to true, and you can actually view the output of your track reference. So that means you can actually watch it increase, go from 4 to 8 to 12, so on and so forth. Otherwise, all you get to see is that over time that output happened. And then mins and maxes can be set so that it essentially, once it hits 60, you never want it to go above that. I might set a max of 60. Otherwise, it'll continue to run afterwards. Another arithmetic block is the PI controller. Pretty standard. You put in a set point of what you're chasing. You run in an actual signal into the input side, and then you can actually specify gains and integral times. Same thing before. Tracks allows you to track over time as we go, and mins and maxes allow you to make sure that your values never exceed thresholds that you've set there. So you can program a couple different ones of these into the actual adaptive programming. What we had mentioned before is, some of this code is very, very, resource intensive. PI controllers would be a good example of something that takes a lot of memory from the program. So adding 2 or 3 or 4 of these into the blocks might actually just take up all your memory at that point, and you're not able to build things. So be aware of that. A lot of times, the bigger the block is, or the more complicated the control is, the more memory it takes up when you load it onto the drive. All right, that wraps up arithmetic blocks. Jumping into the logical blocks. We got really basic logic, ands and ors, zors and nots. Zors basically being if only one input is true, then the output will be true. If both inputs are true or both inputs are false, then the outputs will be false. So it requires just one of the inputs to be true. And then nots are inversing everything, are inverting it, so it's flipping it back. Ands or ors, pretty self-explanatory. I'm not going to jump into that one. All right, continuing with the logical blocks, we get into bitwise logic. Bitwise logic function blocks are very, very similar to the logic blocks we already talked about, the ands, the ors, and the zors, but they allow for other values other than true and false. The two things to note here is because I'm allowed to use floats because of that rounded input that you can see there, that's gold. All negative values or values above 2.1, that's about 2.1 billion, which is 2 to the 31st minus 1, will be evaluated as 0. So that's something to consider here. And then the lowest 16 bits of the result is always taken. So if I ultimately do the ands and the ors and the zors and it grows above 16 bits, I'm only going to be able to pass out the first 16 bits of whatever that result would be and written to the output. A couple more logic blocks. We got some triggers. We got a trigger up and a trigger down, and those ultimately are going to change the instant you have a change. So I'm just going to talk about trigger up for now. Output's true when the input changes from false to true. All other times it's false. So it's pretty instantaneous. It's going to run that one time. It's going to be every time your digital input flips on to high, it's going to trigger once and then it's going to turn back off. You only want it to run one time. And then you have an SR relay, which is essentially just a latching relay. So I listed a couple examples of how that logic works, but you have two inputs. You have a set and a reset, and then you have an output. So it's always going to be looking at the previous output when it's doing all of this. So, in comparison, I'm going to be looking at the previous output. So let's say it was outputting 0. I reset at false. My set is 0. My output would be 0. If I was 0 and I set to 1 and don't reset, my output would be 1. If I reset at any given time, it's going to set back my output to be false or 0. And then I give the last couple examples down there. If my previous out is 1 and I do nothing, it's still going to stay 1. If my previous out is true and I set it again, so I send a high signal to set, I would still stay as 1 as my output. So pretty nice functionality. This can be used to add some emergency capabilities to the drive, make sure somebody resets a button, presses a button, something like that. But latching relays built in, so you don't have to build up some complicated logic to make that work, which is typically how you would try to make that work otherwise. You get into some selection blocks now. So you have basic selectors, you have your mins, your maxes, and your limits. So pretty self-explanatory on the first two. You get to put into 8 maximum inputs, and it's, in the case of min, it's always going to pick the lowest input, max always going to pick the highest output. And then you have limits. So outputs the in, but limits it by the min and the max. So ultimately, I can take any number. Let's say I'm feeding it the number 23. My max is 20. My min is 0. I would have an output of 20 at that point because it would get cut off because of the maximum. So pretty nice feature. More advanced selects. This allows you to put 8 different inputs in and then select which one you want. So first, I give a couple examples there. So if I have selection is equal to 1, then the output is equal to whatever is the input of 1. If the selection is equal to 8, the output is always going to be whatever the input is to 8. There is one exceptional case here. If select value is 0 or the input doesn't exist, let's say it's 79, I feed that, then the output will be 0. So some switches now. So the value written into the output is in X. So you can see that in X isn't on there, but in X would be in 1, in 2, etc., etc. Whose select X is set first. So you see a couple of those select 1, select 2s, etc., etc. As soon as one of those become high, that's what's going to be the output. The in 1, in 2, etc. is going to ultimately be the output. If no select X is set, then the default input is written to the output. So you have a default at the very bottom. This is another one of those you can drag down and have up to 8 different inputs. So I ran through a couple different examples here with 3 selects. So let's say my first one is all the select 1s are set to 0. The output would be that default input. Let's say select 2 and select 3 are high or true. Input 2 would ultimately be the output at that point. Select third example, third row down. Select 1 is high, everything else is false. Input 1 would be the output. Everything's true. Input 1 would be your output. And then last but not least, only select 3 is true. You get input 3 as your output. Pretty self-explanatory, but I think using some of those examples there make it a lot easier for you to see it and understand it. All right, a couple comparison blocks. So similar to the logic blocks where I'm just comparing them back and forth or looking at functions here, I can actually look at things to make sure if certain values are greater than, less than, or equal to. So in my case, let's look at greater than first. I have 2 inputs as A and B, and then I have HYST, the hysteresis. So compares if value A is greater than B. If it is, then it's going to say true. Then you can also add an optional hysteresis, and that's subtracted from B. So if I say A is equal to 5, and I say B is equal to 3, and my hysteresis is 2, essentially my math would be saying 5 is greater than 3 minus 2, which equals 1 at that point. So I would have a true output. I could also tweak that around a little bit more and say A equals to 5, B equals to 6, right? Just a little bit higher. And my hysteresis is 2. I'd essentially be saying now 5 is greater than 6 minus 2, and I would still get a true output from that because 5 is greater than 4. Less than works the same way, but the hysteresis is added to B instead of subtracted. And then equal just compares that the 2 values are equal there. That would be another one that would be nice to have a hysteresis added. I've had that a couple times where it's needed. But ultimately, if you need something like that, you just add an add block before A or B or subtract block if that's something that you need. Get into some of the timer blocks. These are the 2 basic ones. There's T on and T off. So when in is true, the output will be true after the delayed seconds have passed. Same thing with the off. When in is false, the output will be false after the delay has passed. Very, very basic, very simple. So now that we've covered the basic timer blocks, let's talk about some of the more advanced timer blocks, like state timers. State timers basically run through the different states based on the inputs that you define into the time inputs, which are floats, and it would output the current state based on how it's cycling through all of this. One thing to note is that the timers can be paused and the state can be reset anytime you want to do this. So I'm going to walk through a quick example here. I really like using examples with little tables. My example, I use two timers. I use time 1 equals 2 seconds, time 2 equals 1 second. And then I output a little table here with some time across the bottom on x-axis. And then I show my states where my reset and my enable are inputs on my block. And then my output is just what state I'm going to be in. So at time 1 second, or I guess time 0 seconds, I enable, or I started the clock and put a high signal on enable. This starts to run for 2 seconds, and I'm outputting 1 this entire time because I'm in state 1. It runs for the 2 seconds defined by time 1, gets to the 3rd second, and it continues to be enabled. So now it switches to state 2 and outputs that on the function block. We enable for a 4th second, and it switches back to time 1 or state 1 because I've run for the 1 second defined in time 2. We continue to run this, we're still enabled, but at 6 seconds, I remove that enable signal. And what you'll notice is I went 1, 1, 2, 1, 1. I would have expected a 2 here had this just continued to be enabled, but because I took that signal away, it's now paused the timer and I stay at state 1. At stage 4, I actually go out and reset the timer and then enable it again. So in this case, because I reset it, it automatically went back to 1, even though I was expecting with the enable for it to go to 2. Because I reset it, it reset to 1. I then continue to run this on enable for the rest of the way, and I see the standard cycling that goes on. 1, 1, 2, 1, 1, 2, 1, 1, 2, 1. So here's 4 milestones that I kind of wanted to highlight of how this worked. I think we did a pretty good job of illustrating that. Now I get into some of the get bits functions. So this is an operation block. So first and foremost, get bits. What you have the ability to do is input a float up at the top, and then you get to specify which bit you want to grab from that number, and then output that as either true or false on the output. So in my case, for our example, we use the input as being 53,943, which in Boolean is that long string of ones and zeros there. 1, 1, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 1, 1. So that's a 16-bit number. That's the output there. So I've went through 4 examples down at the bottom. Let's say I have bit 1. Bit select 1 is set to 12. Bit select 2 is not specified. Bit select 3 is not specified. Going up to my little conversion from float to Boolean up above, I look at bit 12. That was set to 1. So I'd be 1, 0, 0. My output would be 1. Example 2, I still am looking at bit 12, but then I add bit 2 as looking at bit 9, and then I also look at bit 3, which is a 0. So I have 1, 1, 0. That's going to output a 1 because it's essentially triggered as an OR statement, or it's evaluated as an OR statement when multiple things exist there. Example 3, I'm looking at bit 13, which is a 0, bit 10, which is a 0, and bit 6, which is a 0. So my output would be 0 or false. And then the last example, bit 4, I have bit 13, which is 0, bit 9, which is 1, and then bit 6 is my last select, which is 0. That would output 1 as well. A lot of times I use these when I'm using the data storage and I'm storing things into the drive. I have the ability to essentially store 16 additional parameters that are set as true, false into the drive. So something you should consider in the future with that. Vice versa, we have set bits. Works exactly the same way, but there's 2 different set bits. There's set bit 0 through 7 and set bit 8 through 15. And basically that's taking either set bit 0 through 7 is taking the first 8 bits of my number, and then 8 through 15 is taking the last, I guess it's the last 8 of the number. So using the same input of 53,943, my inputs are still kind of the same, but it breaks down that if I use set bit 1 in that, or 0 through 7 here, I change my bit X's to XX0, 110, 110, 11. What you'll notice that my output switches any of the states where bit X is true where it wasn't before. So it's essentially setting all those numbers, and I'd see an output of 53,979. So what that float would be, set bit 8 through 15, saying the exact same thing, but then just running through a bit X set to 111, 11011 would result in an output of 64,439. So in this case, I'm specifically setting each specific bit. The float piece doesn't matter so much when I'm using this. It just stores the data. That's the data type. I ultimately, anytime I start using set bits and get bits, I'm really just using it for the binary numbers that exist. It just so happens to be a lot easier to show the decimal number when showing some trainings, but I really only care about the specific bits once I start looking at these types of function blocks. And the last set of operation blocks are the connect blocks. These are ultimately connects for the booleans and connects for the floats. Oddly enough, this is something that doesn't seem like it would have a lot of use, but every program I've ever written, I scatter them throughout because there's going to be a time where I can't connect one thing to the next thing. A lot of times, if I wanted to take a DI into this, I can then split that out and send it to 3 or 4 different places and have that affect 3 or 4 different blocks is one of the main reasons you use these. But these are literally just, it passes the same info in and out, and it's there for you to connect pieces that you might not have been able to have connected previously. So that concludes our overview on adaptive programming. I'd like to spend the last couple minutes walking through a really quick example application. We're going to look at doing a cooling tower controller, building that all in to the actual drive itself. So let's look at a quick overview of what we're trying to do here. We're trying to build a quick 2-stage cooling tower controller. In my specific example, I'm using a 15 horsepower fan, which I'm going to control with a VFD, 7.5 horsepower spray pump, which I'm going to control with an across-the-line starter, an 11 kilowatt basin heater, an electronic water level controller, a vibration cutout switch, and a temperature sensor are all required here. I'm going to have 2 different stages. In stage 1, I'm going to have the fan off, but I'm going to be running the spray pump to run water through the fill. And then I'm going to expand on that in stage 2, kick on the fan while running water through the fill at the same time to get some of that cooling that we require there. Some of my other points I want to mention is minimum on times are required for each stage. I don't want to have it that it's cycling back and forth really quickly, so I've got to program that into there. I also want to have it that the basin heater will have an auto off switch, which will be controlled by the drive. Ultimately, I don't want to run a basin heater if there's no water in it. Middle of winter, I've already drained it. It doesn't make sense for me to run that or have that basin heater heating up the water at this point. And then last but not least, the EWLC and the VCOS will be set up like interlocks. So something to consider here. I showed kind of an example of a curve of what we were trying to do here. I have the operating range, operating through that. It hits into, stage 1 to kick on the spray pumps. It then jumps up into stage 2, kicks on the main fan, and I saw it dip again right here. Well, that's where that minimum on time is required, that I'd like to keep stage 2 on for a short period of time because you see all of a sudden all this, it still continues to heat up. But then I have stuff drop off. Once it drops below the lower deadband number, I wanted to turn off completely and then watch it just kind of run through the operating range again. So this isn't real data, but this is essentially my temp sensor. I just wanted to show you how we want this to cycle through. So I broke this down a little bit further for everybody. I looked at all of our different I/O and spelled out exactly what we were trying to do here, looked at some of the different parameters that we had available to us, and then I also started defining some of our data storage so that we didn't utilize what's not available or what's available on the drive. In this case, I have data storage, 4 data storage units or items on an ACH580, so I'm going to utilize all 4 of them actually to accomplish this program. So on the digital inputs, the first thing, DI1, remote start input, pretty standard. DI4 is when I want the basin heater to be in auto mode. DI5 is going to be my water level cutout control, and that's reversed. So basically, I'm looking for a high signal there in order for my drive to run. AI2 is going to be my temp sensor. RO2 is how I'm going to turn on that spray pump controller or the across the line starter. And then RO3 is how I'm going to turn on the basin heater at that point, that contactor, pull that in. A couple different parameters I want to look at. I actually want to utilize some of the PID functionality built into the drive. I'm not going to expand on or build my own PID controller, just use what's in the drive. So the first parameter I want to look at is 1222, which is the temp sensor value, which is being fed into AI2. And then the next one is parameter 40.3, which is the set point. That's what I'm trying to chase after. That's where I'm going to program that I want to be at 75 degrees or 80 degrees or whatever it needs to be. Data storage, all 4 of them. First one, data storage 1, is going to be our deadband. That's going to specify the range around the set point, which nothing happens. So I'm usually going to set that to maybe 2 or 5 degrees. Data storage 2 is my limit. This defines when stage 2 starts or to shut down. So this is going to be the limits that I set around my operating time. Data storage 3 is going to be my minimum on time. So that's usually going to be in seconds. Maybe 30 seconds is the time I want there. But I can program this all right from the keypad. I don't have to go in there and program it any differently now. I can actually, do this during startup, make things easier, or even load it in with a custom parameter set. And then the last one I'm using is my bit status storage. In my case, I'm using only the first bit, which is 0, and I'm going to say shut down all as 0. I'm storing some data there. We could also store more data into bits 1 through 7 if we wanted to, but in this case, I'm just storing 1. So let's start looking at the breakdown of the program itself. Adaptive programming is built into 2 different sections. There's the base program, which just runs constantly, and then there's the sequential program, where it bounces from section to section to section, but the programming has to say you have to go back to sequence 1 or sequence 2, and that'll make a little bit more sense when we talk about the sequence, the control sequence that we want to break down for our cooling tower controller. But in the base program, I want to look at some controllers and things that are going to be done and constantly being monitored all the time, and it doesn't really matter where we are in the sequence. I just want it to function correctly. So I'm going to put my basin heater controller and my shutdown all controller all built into the base program. So first thing I want to do with my basin heater controller is turn it on if the temperature sensor reads less than 40 degrees F. I don't want that water to freeze, and I want the low water cutout input is off ultimately at this point. So let's look at that code real quick. So I've put in an and statement to go look at the basin heater, which is on digital input 4, and I'm also looking at the electronic water level controller, and you'll see I inverted that, right? Because I'm always looking for the negative, and that'll output to the basin heater. But you'll notice that I have another input here. What else did I have to take into consideration was that temperature sensor. I'm going to use a greater than function. Go look that the temperature sensor is if it's greater than or less than 40. So in this case, I'm saying is 40 greater than whatever the temperature sensor is reading at this point. If 40 is greater than the temperature sensor, it's going to say trigger this on. If the basin heater is allowed to be on or it's in auto mode, then that'll be on. And the water is showing that there's water, then I would kick on my relay output, which then would turn on my basin heater motor starter. Pretty straightforward, pretty simple. 2 blocks. I've already programmed that in there. No extra relays, no extra timers. Used everything on board to the drive. Let's look at the shutdown all. This is any time the temperature sensor drops below the set point minus that limit, that lower limit we were talking about. This is even simpler. So we have our first thing we want to say is less than the temperature sensor. But I need to do some subtraction. We could also do this with the hysteresis, but it would require us moving some logic around. It was a lot easier to actually build in just a separate subtract versus trying to, do the hysteresis. If you remember with less thans, the way that one works is it adds the hysteresis to the number in B, and then compares to make sure that A is less than B plus HYST. So that's actually the opposite of what I'm trying to do here. I want to take the set point and I want to take the limit. I want to take the set point and subtract that from the limit and compare that to the temperature sensor. So that's why I did a subtract there. Then ultimately, if you remember, data storage 4, 0 is what we want to write to say, is this true or false? Should we shut down everything? So this is just kind of our emergency. This is looking to see that all of a sudden the temperature dropped below a certain temperature. It wants to shut everything down. It just runs and shuts it all off. Let's look at the sequence programming a little bit. We got to break this into the couple stages, the operating range, how we want this to work. So the blues are telling us what I should be doing in each one of those ranges. So in the operating range, I don't want the spray pump on. I only want to go to stage 1 if the temperature sensor is greater than the set point plus half of that deadband that we already talked about. If that is met, it's going to jump up to stage 2. It's going to turn off the fan motor, make sure there's no fan motor on, but the spray pump will be on based on if the heater controller allows the spray pump to be on. So that influences it. It'll jump up to stage 2 if the temperature sensor exceeds the set point plus the limit, or it'll go back to the operating range if the temperature sensor is less than the set point plus half of the deadband, and the time it's been in that stage exceeds the the minimum time in that stage requirement. In stage 2, I turn on the fan motor. So my spray pumps are already turned on. I also turn on my fan motor, and I'll only go back to stage 1 if temperature sensor is less than the set point plus the limit, and the T stage is greater than that stage minimum. So this is just me kind of writing out the sequence program in a little more visual way. Let's look at how this all works. So first and foremost, operating range. There's that connect. I said, hey, it's crazy how often you'll end up using this. Ultimately, the first thing we did with this was we fed 0 into, bit 0 into a connect, which then writes that out to spray pump. And I'm sorry, that's not a bit 0, that's the number 0. That's us turning off the spray pump. If you recall, back on this slide, we don't want the spray pump to be on in the operating range. So first thing I do, turn off the spray pump. Next thing is we look, how do we want to end up in stage 2? So I want to make sure that the temperature sensor is greater than, if we recall, half of a number. So in this case, it was the deadband divided by 2. Is what I want to make sure is different here. I'm going to add that to my set point and then compare that to my temperature sensor. Ultimately, if my temperature sensor is greater than the set point plus half of the deadband, I'll end up in sequence 2 of my sequence program. So now I'm in sequence 2, which is stage 1 for us, and I'm looking at the next thing. Temp sensor is greater than, what is it? The limit plus the set point. We had already spelled that all out. Go to sequence 3. Pretty easy. We do a connect again here. Turn off ext1. Now we're going to go do our check to see if we need to go back into the operating range. So we have to have an AND condition, because remember, we need to meet the time in the minimum stage. We're going to do our less than comparison of the temp sensor plus half of the deadband plus set point. If that happens, that's true. But remember, we also have to take into consideration some of the time. So look at my time on, make sure it's meeting my minimum time, and I will run it that way. So the first thing this is doing is seeing, hey, am I being told to be shut off at all? If I'm not being told to shut off, then let's keep running. Run the spray pump, which is what that's doing here. Then it's checking to make sure that the spray pump's been on for at least the minimum time before it's allowed to go back to sequence 1. But let's say we exceeded our temp sensor and our limit, and we go up to sequence 2, which is sequence 3, which is stage 2 for us. Stage 2, starts off with us figuring out, well, when will we have to go back to stage 1 or sequence 2? We see that minimum time. There's that timer requirement. So that makes pretty much sense. We've already talked about that. Keep building in. Now we've got our set point plus our limit. Is that less than, or is temp sensor less than the set point plus the limit? If that's the case, it's going to be true. So we'd have true again here. And we want to make sure the time is there as well. I'm sorry, not the time. In this case, we're making sure it's not being told to shut off. So I look at data storage 4, look at bit 0, connect it in. I tell the motor starter to start, and then I tell the fan to start. That's what I'm telling them here. I come in and then check to make sure if the temperature ever drops, drop down to stage 1. And that concludes our overview and quick example application of adaptive programming, which is part of ABB's all-compatible portfolio of drives, including the ACH580, ACQ580, and ACS580.